Pluto and Neptune. Is a collision possible or pure speculation? Once recognized as the ninth planet in our solar system, Pluto remains a fascinating and mysterious dwarf planet located far from Earth. Despite being reclassified, it continues to captivate scientists and the public alike. Recently, bold claims by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited interest in Pluto. They've suggested that this frozen world might be on a trajectory that could eventually lead to a catastrophic collision with Neptune, raising urgent questions about the plausibility and potential consequences of such an event. Is this theory a dramatic overstatement, or is there a real reason to be concerned? To explore this, we must first understand Pluto's unusual behavior in space. Initially classified as a planet, Pluto was later redefined as a dwarf planet due to its small size and highly irregular orbit, a decision that remains a topic of debate among astronomers. Recent studies have highlighted that Pluto's orbital path crosses Neptune's, which on the surface appears to be a recipe for disaster. Pluto's orbit is unlike any other. It takes approximately 248 Earth years to complete one full orbit around the Sun, meaning Pluto hasn't even finished a single revolution since its discovery in 1930. Its path is highly elliptical and tilted about 17 degrees compared to the relatively flat orbits of other planets. Even more intriguingly, Pluto's orbit actually brings it closer to the Sun than Neptune for about 20 years during each of its lengthy revolutions. This anomaly raises the obvious question. If their orbits cross, why haven't Pluto and Neptune collided? The answer lies in the intricate gravitational ballet of the solar system. After Pluto's discovery, astronomers noted the strange nature of its orbit. Despite its inclination and eccentricity, Pluto has managed to maintain a stable trajectory for millions, if not billions, of years. This stability is largely due to gravitational interactions with other celestial bodies, especially massive ones like Jupiter. These forces help prevent chaos by keeping Pluto in a resonance with Neptune that ensures they never get too close, despite their overlapping paths. This dynamic can be explained in part by the three-body problem in celestial mechanics, which describes how the gravitational influences of three bodies, like the Sun, Neptune, and Pluto, can create complex, often unpredictable motion. Even slight variations in Pluto's initial conditions could, in theory, lead to major changes in its path over long timescales. Yet simulations show that Pluto's orbit has remained remarkably steady, suggesting that it is less chaotic than it may appear. Jupiter's immense gravitational pull plays a key role in this balance, acting as a cosmic regulator that helps maintain the stability of Pluto's orbit and the broader harmony of the solar system. While Pluto's orbital behavior does blend elements of both order and unpredictability, current evidence and advanced modeling strongly suggest that a Pluto-Neptune collision is not a realistic concern. The gravitational mechanisms at play have kept them on safe trajectories for billions of years, and there's no indication that this will change anytime soon. In conclusion, while the idea of a dramatic planetary collision stirs the imagination, science tells us that such a scenario is extremely unlikely. The cosmos, while mysterious, often operates with stability that defies our initial assumptions. While experts like Neil deGrasse Tyson and Michio Kaku offer valuable insights, they also highlight the unpredictable nature of space events, making long-term forecasts inherently uncertain. Concerns raised by astrophysicists about a potential collision between Pluto and Neptune may seem improbable, but they have nonetheless sparked public interest. If such a collision were ever to occur, the consequences for our solar system could be catastrophic. Pluto, due to its small size and icy composition, would likely be destroyed by the impact, releasing a tremendous amount of energy. The resulting debris could pose risks to nearby celestial bodies, potentially even Earth. For Neptune, the collision might significantly alter its atmosphere and orbital path, depending on the specifics of the event. Michio Kaku, a renowned theoretical physicist, brings a unique perspective to this discussion. His research in string theory and celestial mechanics suggests that Pluto's orbit can provide crucial insights into physics underlying space travel. By studying the gravitational forces that shape Pluto's trajectory, scientists can improve predictions of potential space threats and enhance strategies for exploring distant regions of the solar system and beyond. Pluto's orbit also offers broader implications for understanding dwarf planets and trans-Neptunian objects. Its complex and highly elliptical path challenges conventional models of planetary motion, reminding us that the dynamics of space are far more intricate than we often assume. The interplay between celestial mechanics and string theory underscores the importance of understanding how planetary bodies interact. A Pluto-Neptune collision, though extremely unlikely, would mark a monumental event in cosmology. It could provide an unprecedented opportunity to test predictions from string theory under extreme conditions. The energy release might reveal insights into behavior of elementary particles and fundamental forces, core interests in theoretical physics. Although Earth would likely remain physically unaffected due to its distance from the outer solar system, the scientific implications of such an event would be profound. It would offer a rare chance to study the universe's fundamental properties and deepen our understanding of the forces shaping it. Pluto's unusual orbit continues to intrigue astronomers and space enthusiasts alike. The ongoing debate surrounding its classification as a dwarf planet has only heightened interest in its role within the solar system. The concerns voiced by Tyson and Kaku underscore the complex gravitational interactions at play and the importance of orbital mechanics in comprehending the solar system's architecture. Unlike the nearly circular orbits of other planets, Pluto follows an elliptical path with a steep inclination, crossing Neptune's orbit at certain points. Yet despite this, gravitational forces, particularly those from Neptune, have helped stabilize Pluto's orbit over centuries. Still, predicting its future behavior remains a challenge due to the inherently dynamic nature of space. Understanding Pluto's orbit, a window into the outer solar system. The study of celestial bodies remains a complex and often unpredictable endeavor. The theoretical possibility of a collision between Pluto and Neptune, however unlikely, highlights the intricate gravitational dynamics that govern planetary motion. While such an event is improbable in the foreseeable future, the interactions between these two distant worlds underscore the delicate gravitational balance within our solar system. Pluto plays a critical role in helping scientists understand planetary evolution and celestial mechanics. NASA's New Horizons mission, launched in 2006, revolutionized our view of Pluto with its historic flyby in 2015. The mission delivered groundbreaking images and data, revealing vast nitrogen ice plains, towering mountains of water ice, and a surprisingly active geology. These discoveries significantly enhanced our knowledge of how distant planetary bodies form and evolve. The success of New Horizons showcased not only technological achievement, but also the power of international collaboration in space exploration. Insights gained from Pluto and its 5 known moons offered a fresh perspective on the diversity of celestial bodies beyond Neptune. These findings have profound implications for future missions targeting other dwarf planets and trans-Neptunian objects, TNOs, deepening our understanding of planetary formation. Pluto's reclassification as a dwarf planet also sparked meaningful debate about how we define celestial bodies. This redefinition is part of the broader, evolving conversation in astronomy about scientific classification. Studying Pluto's orbit has yielded valuable insights into celestial mechanics, particularly as space agencies push the boundaries of exploration into the outer solar system. One of the most intriguing aspects of Pluto's motion is its 3:2 orbital resonance with Neptune, meaning Pluto completes 2 orbits around the Sun for every 3 of Neptune's. This resonance ensures that, despite their orbital paths crossing, the 2 bodies never come dangerously close. Instead, they are locked in a gravitational dance that keeps both orbits stable. This elegant synchronization illustrates the precision of celestial mechanics and shows how seemingly chaotic systems can maintain balance over astronomical timescales. Without this resonance, Pluto's eccentric and inclined orbit, tilted compared to the nearly circular orbits of the 8 major planets, might have led to disruptions or even a collision. Understanding this orbital relationship not only helps scientists predict future behavior in our solar system, but also informs how similar dynamics might work in exoplanetary systems. Pluto also resides in the Kuiper Belt, a vast region beyond Neptune filled with icy bodies and dwarf planets. It is the largest known object in this belt, and its orbit provides clues about conditions in this distant part of the solar system. Kuiper Belt objects, KBOs, and other TNOs are considered remnants from the early solar system, and studying them offers a glimpse into the environment in which our planetary system formed billions of years ago. New Horizons' exploration of Pluto's surface and atmosphere revealed a surprisingly diverse and dynamic world. Features such as frozen nitrogen plains, towering ice peaks, and evidence of atmospheric processes suggest ongoing geological activity. The mission also provided data on Pluto's moons, offering insights into how satellites form and evolve in the outer solar system. The mission's success reignited scientific interest in exploring the Kuiper Belt and beyond. As space technology advances, new missions are being designed to target more distant objects, potentially unraveling even deeper mysteries of our solar system's past. Despite Pluto's apparent orbital stability, its highly eccentric and inclined trajectory raises important questions about long-term planetary dynamics. Its unusual orbit challenges the assumption that our solar system is a perfectly ordered system, instead revealing a more complex and sometimes chaotic cosmic environment. These findings could reshape how astronomers model planetary formation and behavior over millions, or even billions, of years. In conclusion, while a collision between Pluto and Neptune remains extremely unlikely, the study of their interactions offers critical insights into the dynamic and evolving nature of the cosmos. Pluto's unique orbit, its role in the Kuiper Belt, and its gravitational dance with Neptune provide a rich field for astronomical study. Each new discovery helps refine our models, enhances our ability to predict cosmic events, and pushes the boundaries of human knowledge. As exploration continues, Pluto will remain a key piece in the puzzle of our solar system's history and future.